Hello everyone and welcome to Quadratics, Functions and Equations Lesson 7, last one of our quadratics unit. So we are going to take a closer look at the roots of quadratic equations, and more importantly we're going to look at something called the discriminant. So we got a little review here, and it's saying find the roots of the quadratic equation of this equation, x squared minus 8x plus 12, by each of the following methods. So we've actually learned 4 different methods here. By graphing, we can factor that. By inspection, we can complete the square, and we can use the quadratic formula. But how do we know which one of these to use and when? I'm not going to actually factor it. I just think we already know how to do all of that. But here we can talk a little bit about when each method might be appropriate and not appropriate for solving quadratic equations. So first of all, by factoring using inspection or decomposition. Sometimes it doesn't let me scroll with my finger. It mistakes it for a pen, which is super weird. All right, here we go. So factoring using an inspection or decomposition, it works well when the equation is in general form and can be factored into a product of binomials. So anytime we are in general form, ax squared plus bx plus c, you should try to use inspection or decomposition. And if the numbers don't seem to work, like in the last note video there, we saw a trinomial where the numbers just didn't work out. We tried to do decomposition and it didn't work. Then you would use quadratic formula. But if you can use inspection or decomposition, it's a good idea. It's a little bit easier and less of a process. Quadratic formula works for any equation in general form. Especially when the equation is difficult or impossible to factor. So if you can't factor that, or it's just really big numbers and you're struggling, you can use the quadratic formula. Completing the square, we have seen in the past that it doesn't work very well for the general form of the equation, but it works well when our equation is in standard form. And graphing, it always works. However, so always works, but will not give exact answers if the roots are irrational. So a lot of times we're seeing roots that are irrational. We end up with a square root of a non-perfect square, and that is going to create irrational roots. So if you graph it, you're not going to get those exact numbers. There we go. That's kind of an outline of the 4 different strategies. So these 2 you're looking at general form. This one, there we go. This one is when you have standard form, and then graphing works all the time, but I would suggest just using it to check because it's not always going to give you exact answers. All right, so in this lesson, we are going to look at first making sure that we have a quadratic equation. I almost said aquatic equation. That would have been weird. So here you can see that we have our a values in the bottom of these fractions, and that's not what we want. So we want it to look like ax squared plus bx plus c. And we can do that if you say, okay, well, we have 2a squared plus 3a is equal to -1. If you multiply every term by a squared, what's going to happen in this first term, those a squareds cancel out and you're left with 2. In this second term, you have a squared on the top and a on the bottom. So you're just reducing that to 1a. So this one cancels and that squared canceled. And then on the other side, you have -1a squared, or just -a squared. So you can add a squared to both sides. And what you're left with is a squared plus 3a plus 2 equals 0. And we can factor that if we want. So two numbers that multiply to 2 and add to 3 are going to be 2 and 1. So our a values, our roots, are going to be -2 and -1. So that little multiply everything by a squared trick is going to come up a lot in this unit. It's a good thing to know how to do. Okay, let's get on to actually investigating the roots a little bit. Oh man, okay, my computer's being nice and slow. So we are going to use the quadratic equation, the quadratic formula, sorry, to solve for all the roots of three different possibilities here. So we have x squared minus 6x plus 5 is equal to 0. And we're going to plug it into our quadratic formula here of -b plus or minus the root of b squared minus 4ac over 2a. And they've kind of got everything filled out for you except what's underneath the root sign there. So I know in this one, a is 1, b is -6, and c is 5. So underneath our square root sign, we are going to say -6 squared minus 4 times 1 times 5. That all reduces down to +16. So we have 6 plus 4 divided by 2, or 6 minus 4 divided by 2. And when we solve that, 6 plus 4 over 2 is going to be 5. And 6 minus 4 over 2 is going to be 1. So we have two roots, and you can see that when I attempt to scroll, my computer glitches out. Oh man. Okay, you can see we have two roots, right? We have one there and one there, or two zeros. All right, let's do the next one. X squared minus 6x plus 9. So in this case, our a value is 1. Our b value, oh, it's the same. Oh no, our b value is -6, and our c value is +9. So we're going to plug this all into the quadratic formula. B squared is going to be -6 squared plus, not plus, minus 4, 1, and then multiply by 9. And when we punch that all in, that square root is square root of 0. And the square root of 0 is just 0. So now we have 6 over 2 and 6 over 2. So our roots are actually going to be the same in this case. And when that happens, that means we only have one x
x-intercept and what is actually happening with your parabola, if my computer will ever let me scroll, is that the parabola comes down or up depending on if it's a positive or negative and just touches the x-axis and then returns back the way it came. So you get one place where it just touches the x-intercept or touches the x-axis, which is considered an intercept, but you don't cross twice. And the last one we're going to look at is x squared minus 6x plus 13. So your a value is 1, your b value is negative 6. In this case, we're changing the c value to be positive 13. So it's going to be negative 6 squared minus 4 times 1 times 13. And what we get underneath the square root is a negative 16. You cannot take the square root of a negative number. When that happens, when you do get that square root of a negative number, it means your roots are not real. They don't exist. And that's because if you look down, if we graph that, our parabola doesn't actually cross the x-axis. So we don't have any x-intercepts. So we're going to take this into the next page. So the roots of a quadratic equation are represented by the x-intercepts of the graph. So the roots can be they can be equal or unequal, and they can be real or non-real. So in graph 1 that we looked at, the roots were real and unequal, right? I think we had x is 5 and x is 1. Our parabola crossed twice, so they were real values and they were distinct, two different ones. In graph 2, the roots were real and equal. We had the same root, right? We had x is equal to 3, and that's where that parabola just touched that x-intercept. So they're real values, and they're equal, or they're the same. And then in graph 3, we had non-real roots. That parabola never crossed the x-intercept. And you noticed in that equation that we changed nothing except what was under the square root sign. So I'm just going to write the quadratic formula here. So it says the nature of the roots of a quadratic equation can be determined without actually solving the equation or drawing the graph. So we don't actually have to solve this to figure out the nature of the roots. And by the nature of the roots, I mean, are they real and unequal? Are they real and equal? Are they non-real? So you don't actually have to solve them to know that. We can actually just look at the value underneath the root sign. Is b squared minus 4ac. So you can see here the number b squared minus 4ac, which appears under the radical symbol in the quadratic formula, can be used to discriminate between the different types of roots. And it is called the discriminant. That is a word we're going to use often, so don't forget it. So the discriminant is b squared minus 4ac, and we can use that to figure out what kind of roots we have with our quadratic equation. So in the first equation on the back page there, or on the last page we did, our roots were 1 and 5. So the nature of the roots is that they were real and unequal. And our discriminant in that case was 16, and it was a positive value. In the second one, we had 3 and 3 were our roots, or just 3. They were also real values. They were equal, and our discriminant was 0, right? When we plugged everything under that square root, it came out to be the root of 0. And in the third equation, or the third graph, we didn't have any roots. They were non-real. And underneath our square root, or our discriminant, was negative 16, negative value. So hopefully you realize now that if the discriminant is equal to 0, like in our middle case here, then the roots are real and equal. We should only have one root. If the discriminant is greater than 0, like the first graph, our roots are real and unequal. And if the discriminant is less than 0, the roots are non-real. All right. So determine the nature of the roots of the following equations without solving or graphing. So you just got to be careful what the question's asking. Is it asking you to determine the roots or the nature of the roots? The nature of the roots is a little bit easier to figure out, because now we can say, okay, well, if we're looking for the nature of the roots, we just need to know the discriminant. So in this case, we can say, well, A is 6, B is -1, and C is -1. And we know the discriminant is just b squared minus 4ac. So it's going to be -1 squared minus 4 times 6 times -1. -1 squared is 1, minus 4 times 6 is 24, times -1 is -24. When we subtract a negative, it's like adding. So our discriminant is positive 25, which means our roots are real and unequal. We're going to have two distinct roots. Same thing with the next one. First thing we want to do is get everything onto the same side of the equation. So we have x squared minus 8x, because we're going to subtract 8x from both sides, plus 16 is equal to 0. That means our a value is 1, b value is -8, and c value is 16. So we can find the value of the discriminant. It's going to be b squared minus 4ac. So now we have -8 squared minus 4 times 1 times 16. And when we plug all of that in together, we are going to get 0. So when our discriminant is 0, we have our roots are real and equal. So we're going to have one root. And then the last one, a is 5, b is 2, and c is 1. So our discriminant b squared minus 4ac is going to be 2 squared minus 4 times 5 times 1, which is going to be 4 minus 20, which is -16. So when our discriminant's negative, our roots are non-real. That means our function sits either above or below the x-axis. Determine the value or values of m the quadratic equation x squared minus 8x plus m has to be real and distinct. So we know that if we want it to be real and distinct, we want a positive discriminant. So in this case, our a is 1, our b is -8, and c is m. So we can plug that in. We know it's going to be b squared minus 4ac. So it'll be -8 squared minus 4 times 1 times m. So our discriminant becomes 64 minus 4m. And we want it to be greater than 0. So we can say this has to be greater than 0. And then we can solve for m. And when you do this, you just pretend this is an equal sign. So you do algebra just like that's an equal sign. So in this case, we are going to subtract 64 from both sides. And then we're left with -4m greater than -64. Divide by -4. And now we have m has to be greater than -64 divided by -4 is 16. Wait, did I flip my signs here? What happened? M has to be less than 16. What just happened here? Oh no, I made a mistake and I can't figure out what I did. All right. M has to be greater than 16. Something flipped around here and I can't figure out what's going on. I might have to figure this out and then come back to you guys. Hopefully the process makes sense. Something flipped and I don't know what happened. Okay, let's carry on for now. There's no point in you waiting for me to figure it out. All right, so let's move on to the next one. State a condition for, so the next two over here are the same process, but obviously I can't figure out this one. Something's gonna go wrong with these two maybe, so yeah, we'll just leave it for now and we'll figure it out in class. That's weird. Maybe the answer in the book is weird, I'm not sure. So state a condition for b squared minus 4ac so that the equation ax squared plus bx plus c has real roots. Well, we know that in order to have real roots, we need this to be greater than or equal to 0. So b squared minus 4ac is greater than or equal to 0. That's all that we have to do for that one. Given that the equation ax squared plus bx plus c is equal to 0, has real roots, state the condition so that the roots are rational and irrational. So in order for this to be rational, our discriminant has to be a perfect square. Anytime we square root a number that's an imperfect square, like square root of 37, we're going to get an irrational number, 6.12, on and on forever. But as soon as it's a perfect square, we get 6. So that means our discriminant has to be a perfect square. So for I, b squared minus 4ac has to be a perfect square. And if we want it to be irrational, then b squared minus 4ac has to be an imperfect square. Cool, I think I'm going to leave that one there. I don't want to go too long. This is going to bother me until I figure it out, so I'm going to go do that right now. But I won't punish you by figuring it out in the middle of the video. So, have a good day. Don't forget to like and subscribe. You're done, Quadratics. Hooray!